Hi everyone, Tim the Plane Man here, and welcome to Plane Time ArduPilot debugging with VS Code edition. One of the ArduPilot developers, my friend from Shenzhen in China, added a really useful little feature to the WAF, the tool. I don't know what even WAF stands for. WAF is the way you run ArduPilot. So WAF has a set of configuration parameters that you need to use when you configure your development environment for building. And he's added this really neat little feature here, which I'll just show you, is --VS launch. After you clone your ArduPilot repo, you want to run this parameter just once. It will generate, and I'm going to be very careful here, I'm going to not run it because I've already run it once. So you run it once and it generates this file here in your clone, which is a non-checked-in file. It's just a local file and it's not part of the check-in. And it's called launch.json, and it contains all of the information that you need to create to debug ArduPilot. Now what it will do is it will create this debug configuration called ArduPilot. And what I've found is that works great if you just want to do just a basic run. But what I want to do is debug running with RealFlight. So I have RealFlight, as you can see, running a simulation right now. Hopefully it's not going to crash into the side of the hill. Yes, it's just going to miss. It's not actually running connected to ArduPilot right now, and that's just sitting there waiting. But what I have done is I copied the generated configuration here, and then I created a new one. Oh, it crashed into the hill. That's fine. We'll get to restart it. I created a new one here called ArduRealFlight. And what I did, the changes that I made to make this work are that I changed the current working directory to the directory where I have my RealFlight model set up, so that it actually changes directory in there, and it will run with the existing parameters and configuration of this Erase Griffin SITL model that I use for most of my SITL testing. I also added some parameters here so that the VS Code, when it executes, will connect into SITL. So you have to add this one called flight axis. You add this, I think this is existing SIM address is still there. Defaults, I don't want to load defaults because it's already got all the parameters set up correctly. But most importantly here, you want to add the home address of where the plane is actually, where the SITL location is running. I run SITL usually, RealFlight, when I'm doing SITL, I run it in the location called Castle, which is in the middle of the Sierra Nevada mountains in Spain, because it has very interesting terrain and it causes all kinds of problems for planes not hitting the mountains, as you can see. Well, we want to avoid hitting mountains, so how is that working? And what I want to do right now is I want to find out why TECS is not pitching up as much as it could. It's set so that my TECS parameters, and if I just go into our mission planner here and just show you what's going on with the parameters here. So TECS, in particular, the climb max is increased from 5 to 10, so it should be able to climb at 10 meters per second. And I think that's an awful lot for this plane. I haven't tuned it, but I just want to give it the maximum headroom that it can. And the TECS pitch max is set to 25 degrees. So it should, as far as I can see, be able to pitch up, or attempt to pitch up, as much as 25 degrees up as it tries to fly over these hills. But for some reason, when I'm running the SITL tests, I'm never getting more than about 15 to 17 degrees of pitch up. My theory is that TECS is doing something to reduce that. So what I've done is I've put a breakpoint into my, well, not my code, into the ArduPilot code, and it's here. I put a breakpoint right on this line, which is where it attempts to update the height demand. So what I'm going to do is I'm going to run, and I'll just fast forward through the after I get it running, and I'll show you how you start it. And then I'm going to basically let it run without that breakpoint enabled. So you notice that breakpoint is gray right now, and it's a disabled breakpoint. So what I'm going to do is let it run until I get to the point where I'm trying to pitch up, and then I'm going to try to catch it at that instant and right click and enable the breakpoint, and then grab, basically jump into the code and see how you can use not GDB, but a modern code debugging tool to see what's going on inside ArduPilot as it runs. Could be quite interesting. I hope so. That's why I'm videoing it. So stick around and see if you find this fun. If you don't find this fun, of course, click off. I'm fine with that. And I'll try and put some chapter marks in here so you can click in and see the good bits. Because, well, first of all, the setup is great. That VS Code, VS Launch parameter to WAF is very, very useful. Thanks, HuiBin. And now, with VS Code, let's see what's going on inside TECS and try to understand a little bit about how ArduPilot actually flies its planes. So what we do in order to run this is we go into the run and debug option here in VS Code, and then we select the debug profile, and I want to select the one that I've created for RealFlight, so that's this one here. Now, the other thing you have to be prepared for is when you run ArduPilot, it starts the executable, but it won't actually start until you have a ground station like mavproxy connected and running, which is where if you do the standard testing, either Mission Planner is already sitting there waiting to connect into the executable that runs, the SITL executable, or in the case of simvehicle.py, well, simvehicle.py, if you watch the output when it runs, it starts ArduPlane or ArduCopter or whatever the executable is, and then it starts that in the background, and then it starts an instance of mavproxy. So when you run simvehicle, you're running mavproxy, which is a ground station, and that connects to the ArduPilot. Now, if you're running here in VS Code, you don't actually have anything to automatically start that. So what I do is I have over here a console, a terminal running in bash, and that is set up ready with a mavproxy command line here, which will connect to the executing version of ArduPilot at TCP 5760, and then it will create an output so that, for example, Mission Planner can connect to it. And I want to have a mavproxy console, but I don't need the map because, well, I've got RealFlight and I've got Mission Planner running. So what we do is we start the debug by just clicking there, and you notice that runs up the console, right? And it's sitting there waiting for a connection. Okay, now I don't want to open this in the browser, but what I do want to do is go across here to my bash command line and start mavproxy. And there we go. So mavproxy fires up, the console opens up. Let's just make that a little bigger to use the space, and it will take a little bit of time to connect. Don't worry about you get these no link things, because that's just basically everything getting rolling. Okay, link OK, we're connected. Everything is actually up and running. So what we should be able to do now is come back in here, change to auto mode, right? So as you can see in the console over here, that changed to auto mode, and then we should be able to, now we got pre-arm good, so we can arm. All right, so we're armed and we're running. Now in the background here, because I just don't have enough windows going, I actually have a Mission Planner running as well. And so there's Mission Planner, and this is the mission that I want to fly. It's a very kind of a weird mission because I'm deliberately trying to get it to fly out over to open spaces where it's way above the terrain and then to fly near the mountain, so I almost hit the mountain, because that's what I'm trying to do. So I have this path set up where it tries to, you know, create situations where it might crash if my Lua script wasn't running. And so now I'm just going to go back here into here, and what I want to do is I want to wait until I see in here that it's executing the code that does and it basically tries to pitch up to fly over the mountain. So my Lua script is basically detecting the ground. When it detects the ground gets too close, it attempts to pitch up by setting a high altitude and also throttling up, which is interesting because Trude says I should throttle down, but so far in my testing it seems like throttling up works better. And what I'm going to do is I'm going to wait till it flies over here to this waypoint 7, way out over here, and then comes back, hits waypoint 8, and then as it flies to waypoint 9 is where it should go off the rails. So let's just wait for that to happen, and we'll spin the wheel. This will go fast. Oh, I just want you to notice this is the script that's running, and notice it already did a bit of terrain avoidance while I was talking here, and that's basically what I'm looking for when it does the start pitching and then stop pitching. I need to catch it when it's trying to pitch up over a rise, and then see if I can get jump into TECS and to see what's going on with the pitch up. All right, so we've flown out over a really deep valley here. So the plane is a long way above. Like here we can see altitude error 97 meters. The pitch value here is what we're watching for. And we're looking, and right now that's pitching down because it's basically trying to get closer to the mountain to try and trigger it. So what I'm going to have to do is switch back to here, because I do want to catch it before, as it starts pitching out, but before it actually hits. Right, so it's getting close, and it's trying to pitch up. Right, let's enable the breakpoint. So now we've broken, and notice everything freezes. This is actually very cool, because what happens is, although MavProxy is complaining that there's no link, RealFlight is smart enough to just stop and wait. It's waiting for this to execute. So what we've got here is we've got our maximum climb rate, which is currently set to 10, and our max climb scalar, which I don't see, is 0.95. So that's going to give you a climb rate of probably 10. So let's just step over that line of code, and now we see our maximum climb rate set to 1.87. Hang on, that was climb rate, maximum climb rate 10, and the scalar is 0.187. Then the sync rate, well, we don't care about the sync rate because we're trying to go up, so let's skip over that. If the max sync rate, I don't care. If it's not landing, so here we go. So we're going to say the height demand is the height demand in, and the height demand in the previous height demand. So, and we're doing 0.5 times that. And then we just save that, so we get that from before. So our height demand in is basically 68 meters. So we're trying to go 68 meters above where we currently are. I think that's what that's saying. So we limit the height rate of change because the plane is spinning around doing this in a loop. It's not going to go 68 meters up instantaneously. That can't happen. What it needs to figure out was it can incrementally do to go to head towards being 68 meters above its current height. And so we do some calculations here, and then we apply a first order lag to height demand and compensate for lag when commencing height control after takeoff. Well, we're not doing takeoff, so I don't really know why I care about that. I'm just going to click past this. Is doing auto land? No, we're not doing auto land. So we need, here we go. We're not maximum climb condition, and we're not maximum descent condition. So the maximum climb scalar is 0.22, and we just save that. Well, let's go up and step out of that and see. So we updated the height demand. I'm going to step over that and update energies. So calculate. Okay, here I want to go into this one. I want to go and see what happens when it goes into pitch. So I'm going to step into update pitch, because this is what really counts. This is, okay, so we found out that it seems to be calculating the attempt to update the height, and there was no problems with that. Now it's going to go, it's not using an airspeed sensor, it's not in VTOL mode, it's not under speed or in takeoff or various other things. Okay, so the SPE weighting, whatever that means, is currently set to 1. Okay. So we track the demanded height. So this is where our height demand that we just looked at comes in here. So our height demand is currently 4.62 meters. We think we want to go up 4.62 meters from where we currently are. And so this is the minimum, and then we want to calculate the maximum. So our SPE demand max is set to 98. So now we're getting, so we sum the predicted versus the plus damping correction. So this is where we basically, ArduPilot is doing some things to try and prevent the plane from doing things like pitching up too high so it stalls. And I don't know all the details about how that works, but that's basically what we're doing here. So the pitch damping is currently set to 0.1. That's interesting. What parameter is that? AP param. I just want to see where that is. AP param pitch damp. Let's just find that value. It's pitch damp. It's TECS pitch damp. Okay. That's interesting. All right, TECS pitch damp. Let's see what TECS pitch damp is set to. TECS pitch damp is set to 0.1, which is damping gain for pitch control from TECS. Increasing may correct for oscillations in speed, but too much may cause additional oscillation and degraded control. So it's basically trying to stop the pitch from oscillating. Okay, so I think that's a safety feature, and I don't think that it's going to be a problem. Okay, so now we get our DOT demand total, the inverse of the gain during climate. Okay, let's just step over this. Flight stage is not takeoff. And again, we want to know what the max comes out to. So we've got our integrator for DOT max is 50. And in the comments, if you don't know what some of these things mean, neither do I. I am maybe just know enough to be dangerous here. What I'm trying to do though is I'm trying to figure out what input is causing TECS and this incredibly complex and sophisticated code to not pitch up as much as I want. So to a certain extent, I'm just skipping over the things that I think don't matter. What I'm looking for is something that's an input, a parameter or a setting or some kind of value that has been set in the configuration, maybe as a default, that is preventing TECS from pitching up as much as I want it to do. So the calculation where TECS does the calculation of pitching up, I'm just going to let it do that. What I'm looking for is when something stops TECS from doing what it wants to do, which is why I was interested in that damping value. Was it that damping value parameter that's causing it? Not sure yet, but I don't think so. Okay, so now we get our delta. So we calculate the integrator state, constraining input. We go, constraining input if pitch limits are exceeded. Now this is the part where, so what happens first is TECS calculates this pitch demand unconstrained, pitch dem unc, and that is 0.4. So it's saying from where I am now, I just want to incrementally go up 0.4 radians. And now what happens is that it applies various constraints to see whether or not the constrained pitch that it's going to send out to the motors and to the control surfaces, like the elevator, is going to be that full 0.4 radians. So let's see. Right, so we inhibit integrator, and there is no inhibition coming in from that. Whoops, why is that? It says false. Oh, if it's not. So here we go. So the integrator is just adding the delta, and yes, I don't know what that's doing. So what's our pitch demand here? It hasn't changed fundamentally. It's still 0.4. All right, so now this is where we're constraining the pitch demand. So it's between minus 0.2 and 0.4. So if the unconstrained pitch demand is 0.4, I'm thinking the pitch demand should be 0.4. Yes, it is. So it wasn't limited by that. So these pitch maxes are the TECS pitch min and the TECS pitch max. So that TECS pitch min and the TECS pitch max are these two values here. And now let's go to the next line of code. So if the pitch demand, which we just calculated up above, minus the most recent pitch demand, which is actually higher, is greater than the pitch rate increment, which is the limited version of the pitch increment here, then, so it's not. So here we get the pitch demand minus that is less than, yeah, so neither of those, actually that pitch rate integrator didn't limit anything anyway. So that's fine. So last pitch demand is the pitch demand. Where are we? So we're just doing logging. That's fine. And we're done. Well, that's unfortunate. So I don't see where from that I got my pitch limit. Now let's kick forward in terms of what's going on here. So we update the throttle with the airspeed. Detect for bad descent. Let's just go back up. So we update pitch and throttle, and we're done with that. Well, honestly, that didn't help me much. I don't know why TECS is not pitching up as much as it could. Because look at that. That is going to fly into the side of the hill. And currently the pitch is 15 degrees, but the plane can definitely pitch up to 25 degrees based on, let's just say that again. The TECS pitch max is set to 20. So I think I found something after tracking through all of the TECS code and figuring out that there was nothing in TECS that was restricting what was the pitch that the plane could fly at. What I then thought was, well, once TECS returns the pitch demanded, which was 0.42, and 0.42 is in radians, and that's about 25 degrees, which is pretty much the maximum that was allowed. Where did it go from there? And what I discovered is, what's the message here? Read the documentation. Here in the ArduPilot documentation under plane architecture, what I found here is that after TECS calculates its outputs, the outputs from TECS are fed into the calc nav pitch, roll, and throttle variables in the actual core plane code. Well, when I tracked that down in the code, I found that that code here, let me just show you that code because I just found it. It's in navigation, I think. Calc nav pitch. There we go here. So calc nav pitch in the update speed height, called up potentially in other places, is doing this. And what it's doing is the nav pitch CD, which as you see from the architecture is where the TECS is feeding its pitch demand in, was being constrained. So the commanded pitch coming from the TECS controller was being limited by pitch lim max and pitch lim min. And if I track those values down, what I found is that pitch lim max is defined as this value here, which is the pitch lim max deg variable. It only applies in modes with stabilized limits, and auto is one of those. So what do I find if I look for pitch lim max deg is set to 12. Well, let's see what happens if I set that to 25. And now I'm going to fly that exact same mission. I'm not doing debugging. I'm just going to fly it. So let's see, we'll fire up. I'll just start this. We've got RealFlight running. There goes the plane. Here's our nav proxy console so we can watch the pitch value here. I'll also do something interesting here as well and watch I don't really want that. Terrain and the climb rate. Should do it. I don't really want the terrain value. Okay. There we go. So now we're getting our pitch showing up here in Mission Planner, and we're also showing it here in Nav Proxy. We've got our terrain AGL, so this is our height that we're trying to hit, which is about 50 meters above the ground. And now it's pitching up. And we hit 12 degrees for that. That's a very low rise, so that's not a big deal. Yes, there we go. We are now pitching up 19, 20 degrees. Ah, so good. So good. Oops. And it's flying above, it's flying over, and it's not hitting it, and it didn't hit the hill. Ah. Problem solved. King of Playing Man. Over and out.